Today we're going to be talking about solubility product, and solubility product is a type of chemical equilibrium. This type of equilibrium deals with an insoluble salt, an insoluble ionic compound. So when we write the equilibrium, or the reaction for this type of a compound, we're simply going to show that it slightly ionizes. It is an insoluble salt after all, slightly ionizes to form a silver ion and a chloride ion. When we write the equilibrium expression, which is called the solubility product, then the equilibrium expression is going to be that KSP is equal to the concentration of the silver ion times the concentration of the chloride ion. Remember, since the silver chloride is a solid, it is not going to be included in the solubility product. Another term that we want to be familiar with is the molar solubility of a substance. This is the number of moles of a solute that dissolves to produce a liter of saturated solution. The important thing for us in our equilibrium calculations is that this is X in a Rice problem. So remind yourself that X is molar solubility when we're dealing with a KSP problem. So X is molar solubility. Now the KSP of silver chloride, if you look that up, is 1.6 times 10 to the minus 10th. What that means is if we find some solubility product, or the product of the silver ion concentration and the chloride ion concentration, which remember, if it's not at equilibrium, it's called Q. If that value is less than KSP, what that indicates to us is that we have an unsaturated solution and no precipitate will form. If, however, that product is equal to KSP, then we have a saturated solution and still no precipitate is going to form. However, if that product is greater than the KSP value, then we have a situation in which a precipitate is going to form. So an example problem for solubility product problem is that the molar solubility of silver sulfate is 1.5 times 10 to the minus second moles per liter, and it asks us to calculate the solubility product of the salt. So we know that we're dealing with silver sulfate, which, if you remember, silver is always true plus 1 ion. Sulfate is SO4 with a 2 minus charge. So the formula for the salt is going to be Ag2SO4. We're going to show that ionizing slightly to form 2 silver ions and a sulfate ion. Keep in mind that when we have this insoluble salt here, it is not going to be involved in the equilibrium calculation. And when we first start, we're going to start out with a 0 concentration for the silver ion and for the sulfate ion both. As this proceeds towards equilibrium, we're going to gain 2x in concentration for the silver ion. We're going to gain x for the sulfate ion. So we end up with 2x for the silver ion, x for the sulfate ion at equilibrium. And since we know the molar solubility is 1.5 times 10 to the minus second, and we know that that, remember, is x, then we know that the sulfate ion concentration is going to be 1.5 times 10 to the minus second molar. And the silver ion concentration will be double that, 3.0 times 10 to the minus second molar. So we can now write the equilibrium expression for this particular insoluble salt as being KSP equal to the concentration of the silver ion squared times the concentration of the sulfate ion. Since we now know that the silver ion is 3.0 times 10 to the minus second molar, and that must be squared, and we know that the sulfate is 1.5 times 10 to the minus second, Then once we perform that calculation, we find that KSP is 1.4 times 10 to the minus fifth. Another type of calculation might ask us to calculate the molar solubility of another compound called calcium phosphate, which is Ca3PO4 in parentheses 2. So this calcium is a +2 ion and phosphate is a -3 ion. This also asks us to calculate the solubility in grams per liter, and it also asks us to calculate the concentration of each ion in the saturated solution. Now remember, molar solubility is X, so it's asking us to calculate X. It also gives us the KSP of calcium phosphate as 1.2 times 10 to the minus 26. So starting our reaction, we know that calcium phosphate, as it slightly ionizes in water, is going to form 3 calcium ions and 2 phosphate ions. We know that we're not going to be involving the calcium phosphate solid in this equation, in this calculation. We know that we're going to start out with 0 for both of these at the very beginning of the ionization process. We're going to then add 3x and 2x respectively for the calcium and phosphate ions as the reaction proceeds. So we're going to end up with a relationship of 3x for the calcium ion and 2x for the phosphate ion. We can write that equilibrium expression then as KSP being equal to the concentration of the calcium ion cubed times the concentration of the phosphate ion squared. Since above it showed us that the KSP of calcium phosphate is 1.2 times 10 to the minus 26. We know calcium is 3x from our Rice equation, and that's supposed to be cubed. The phosphate is 2x, and that is supposed to be squared. When we work this out, we find that we have 27x cubed times 4x squared, which again multiplies out to 108x to the fifth. When we solve this for x to the fifth, we get 1.11 times 10 to the negative 28. Solving this for x, we get 2.6 times 10 to the negative 6th. And once again, reminding ourselves, excuse me, I boxed that a little early because that must have units of molarity, moles per liter. This is the molar solubility. Now, in addition to wanting the molar solubility in moles per liter, it also asked us to find the molar solubility in grams per liter. Once we know that it's 2.6 times 10 to the minus 6th moles per liter, we simply need to find the molar mass of calcium phosphate. The molar mass of calcium phosphate is 310.18 grams per mole, which gives us a molar solubility in grams per liter of 8.0 times 10 to the minus 4th. In addition, it asked us to find the concentration of each ion in solution. Recall that the calcium ion was given the relationship of 3x in our last equation. So taking 3x times our taking 3 then times our molar solubility of 2.6 times 10 to the minus 6, we end up with a concentration of 7.8 times 10 to the minus 6 molar for our calcium ion. In addition, for our phosphate ion, recall that it was given the relationship of 2x in our Rice equation. Multiplying that times our molar solubility then is going to give us a value of 5.2 times 10 to the minus 6 molar for our phosphate ion. And that concludes this problem. Going on to the next problem, what is the molar solubility of lead-2 iodide in a 0.5 molar solution of sodium iodide? This is a common ion problem. Look at how this plays out. We have lead-2 iodide, which is Pb2 plus with I minus, so our formula is PbI2. We also have, in addition to that, we have, starting out in the solution, 0.50 molar sodium iodide, the common ion being the iodide ion. So that is also going to be in the solution as we start this process of ionization. So writing our ionization reaction, we write that the lead iodine is slightly ionizing to form Pb2 plus and 2I minus. Again, we know that the solid lead iodide is not going to be involved in our reaction. The Pb2 plus is going to start out as 0, but in this case, the iodide ion starts out with a concentration of 0.50 molar. That's very important in this reaction. We're going to, as we proceed in the reaction, gain X and for the lead ion and 2X for the iodide ion. So we would end up with a relationship of X for Pb2 plus and 0.50 plus 2X for our iodide ion. As we write our equilibrium expression, we find that the KSP for this is going to be the Pb2 plus ion times the I minus ion squared. We know that the KSP, if we look up the KSP for lead iodide, it is 8.5 times 10 to the minus 9th. And that is going to be equal to our X for the Pb2 plus times the 0.50 plus 2X for iodide squared. Remember that we can, in cases where K is very small, neglect X. So this ends up being X times 0.50 squared. When we solve for X, X becomes 3.4 times 10 to the minus 8 molar. Now this is interesting because if you look at the molar solubility for lead iodide, the normal molar solubility of lead iodide is 1.2 times 10 to the minus 3rd molar. So notice that we greatly decreased the molar solubility of the lead iodide when we already had some iodide ion in solution. So that is the effect of the common ion in this case. Our last problem then involves two solutions being added together, 200 milliliters of 0.040 molar barium chloride added to 600 milliliters of 0.080 molar potassium sulfate, and asks will a precipitate form. Now this is very important because if it asks will a precipitate form, then you should immediately think to yourself, I need to find Q. And keep in mind our total purpose of finding Q is to compare to K. Now it does not give us a K value, a KSP value in this instance. But if we mix these two solutions together, let's think about what will form. If we put BaCl2 and add that to K2SO4, we are going to form barium sulfate, and we are going to form potassium chloride. Keep in mind that our barium sulfate then is going to be our precipitate. So since that is going to be the precipitate that's formed, that's what we need a KSP value for. And if we look up the KSP value for barium sulfate, when in doubt, Google it out, we find that the KSP of barium sulfate is equal to 1.1 times 10 to the minus 10th. So this is what we're going to be comparing Q to when we find it. Now the first thing we've got to do then is to figure out what our concentrations of barium and sulfate are in solution. If we have 200 milliliters of 0.040 molar barium chloride, the first thing we need to do is find the moles of that. Now remember, to get the new molarity after they're added together, we're going to need to calculate moles over total liters. And notice that when we get done with this reaction, we're going to have 200 plus 600. We're going to have 800 milliliters. So we must keep that in mind as we do this. So if we've got 0.200 liters, and we've got a 0.040 moles per liter solution of our barium, we end up with 0.0080 moles of the barium ion. We're going to divide that by 0.8 liters total to get 0.010 molar barium ion. We're going to do the same thing for the sulfate ion. We've got 0.600 liters originally of our potassium sulfate. We're going to multiply that by the molarity, and we end up with 0.048 moles of the sulfate. Dividing that by, once again, 0.8 liters total, we end up with 0.060 molar sulfate ion. We are now ready to write our equation that barium sulfate, our insoluble salt, is going to slightly ionize to form the barium ion and the sulfate ion. As we just calculated, barium is 0.010 molar, sulfate is 0.060 molar. Again, we don't care about barium sulfate in this Rice equation because it's a solid. Q, which remember is calculated the same way as KSP, is going to be the concentration of the barium ion times the concentration of the sulfate ion, which is going to be the 0.010 molar times the 0.060 molar, which is going to give us a value of 6.0 times 10 to the minus 4th. Now, remember, getting Q is Finally, so that we can compare it to K, we already established at the top that KSP for barium sulfate was 1.1 times 10 to the minus 10th. What we find then is that Q at 6.0 times 10 to the minus 4th is greater than K at 1.1 times 10 to the minus 10th. Keep in mind that what this tells us is that since Q is greater than K, we will end up forming a precipitate. And that concludes today's notes.